All right, let's see if we can finish off chapter 11 today. Last class we were getting into valence bond theory and hybridization. And we left off talking about sigma bonds and pi bonds, and sigma bonds are end-to-end overlap. This is sort of like shaking hands with somebody. And pi bonds are more like a high five, but then you like grab hands. It's a lot less stable than if you've got a handshake with somebody, you've got a direct connection. It would be harder to pull you apart. If your hands are fully outstretched to the side, like you're going in for a bear hug, and then you interlace your hands with them, that's going to be a lot weaker, and that's our pi bond. So we've got sigma bonds where we've got orbitals, can be s or p orbitals that overlap end to end, and we get this nice direct overlap. For our pi bond, it's side to side, and that tends to be a little weaker than our sigma bonds. We'll see sigma and pi showing up in other concepts later on as well. So for an sp2 hybridization, we've got s and 2p orbitals. That's 3 orbitals. So we're going to expect 3 hybrid orbitals as well, and that's what we see for H2CO. We've got our carbon in the middle. It's got a bond to each of these hydrogens. It's got a sigma bond with the oxygen, and then it's got a pi bond with the oxygen as well, and that's what makes up the double bond. So we might think of the sigma bond as our first bond, and then the pi bond as our second bond. So that's how we get a double bond. And there's some fun features, as it turns out, about double bonds, other than they're a sigma and a pi, and so that's kind of interesting. So because the double bond contains 2 different kinds of bonds, a sigma bond and a pi bond, it makes sense that the pi bond is in the double bond is generally easier to break. So let's say that the single bond has 510 kilojoules per mole to break. The double bond, because it's a sigma plus a pi, is going to be less than double the energy to break. So this is nice because it explains why that is. Let's say that it's 745 kilojoules per mole. These are just made up numbers. So it's definitely increasing from a single bond to a double bond. The bond strength is increasing, but it's not doubled. It's just more because the pi bond isn't as strong as the sigma bond. Other fun stuff with double bonds. Single bonds, because they are end-to-end overlap, the single bonds can rotate freely. So if we're still thinking about handshakes, then in the handshake model, we're cyborgs and our arms can rotate. They can twist in their socket. So the bond can spin because it's just end-to-end overlap. When you rotate it, it stays overlapped. Rotating doesn't break the overlap of this sigma bond. When you've got a double bond, you cannot rotate because of that outstretched arm sort of looking pi bond that we've got. Because these are in the up and down position, and this is in the up and down position. If you rotate that 90 degrees, it's no longer overlapped, and so the bond would break. So rotating would only happen if the bond broke. Because you would no longer have that overlap. And one of the effects that this has is that if you've got something with single bonds, you can have free rotation. Here we've got the carbon-carbon bond, and the chlorines can just freely rotate in whatever order. So having both chlorines down, as we've got them represented on the left, is the same as having one chlorine down and one chlorine up, because they can interconvert. So on the left, or on the right, we've got this, and on the left, we've got this. I'm omitting everything that's not the carbons and the chlorines. But because we can rotate around a single bond, we just rotate this carbon and chlorine and it interconverts to this other form. When we've got double bonds, we actually have different forms depending on whether both chlorines are down or one chlorine is up. So these two are separate, different, distinct chemicals. And you can separate them out. There's lots of examples. I don't have any off the top of my head, but there's lots of examples of different, what are called isomers. It's the same thing, but it's just arranged differently. There's examples of the cis and the trans versions behaving differently. So here, cis means on the same side, and trans means opposite side. And you've probably heard of these in a couple of contexts. The food-related context would be like trans fatty acids or whatever, trans fats, cis fats. You usually don't hear about cis fats, it's just trans fats. These are also the same prefixes for like cisgender and transgender as well. So it still means the same thing, but in this context it means on the opposite side of the double bond or the same side of the double bond. This question has a lot of words in it. A carbon-carbon single bond has an average bond energy of 347 kilojoules per mole. A carbon-carbon double bond has an average bond energy of 611 kilojoules per mole. So 347 for a single, 611 for a double. According to valence bond theory, the one that we're working on right now, why is a double bond not simply twice as strong as a single bond? A double bond is composed of two different kinds of bonds, a sigma and a pi. A double bond is a sharing of two electron pairs, or the carbon-carbon double bond is an exception, and they're usually twice as strong as a single bond. What do we think? It's A. Yeah, because according to valence bond theory, the double bond is two different kinds of bonds, the sigma and the pi. When the sigma is stronger, it's that end-to-end overlap. The pi bonds are the sideways overlap, and that's just not quite as good of overlap. So because they're different types, it's not just doubled. If we somehow got two sigma bonds, then we would expect it to be double. Another hybridization scheme that we can have is if we just blend together one s and one p, that's two orbitals. Our sp hybrid orbital is formed. Since we put in two orbitals, we get out two orbitals. And then the leftovers is the unhybridized p orbitals. Two of the p orbitals are just staying as regular p orbitals. They're not blended, they're the shapes that we normally expect them to be, that peanut or dumbbell shape. The two sp hybrid orbitals are arranged in linear geometry. This is our electron geometry for two groups. So we've got two hybrid orbitals, two groups, it's linear geometry. So they would look something like this. It just looks like a peanut-shaped orbital, but there's one that's sticking out to the left, there's one that's sticking out to the right, and then we're just not showing the small tail because it's overlapped when they're together. If we do a Lewis structure for acetylene has sp hybrid orbitals, and one of the s and one of the p blend together, and after we hybridize, we end up with 4 unpaired electrons, 4 unpaired orbitals. 4 unpaired orbitals in valence bond theory means that we can make 4 bonds. And our Lewis structure for acetylene has a triple bond between the carbons. If we're looking at either of the carbons, it's going to be linear. They've got 2 electron groups on them, so they're going to be at complete opposites from each other, and we'll get a 180-degree bond angle. And this triple bond contains 1 sigma bond, 1 end-to-end bond between the sp orbitals, and it also contains 2 pi bonds, the side-on overlap bonds. So one of them is in an up-down position, and the other one is rotated 90 degrees to that. So it would be the way that it's shown here, the front-back. So we've got the end-to-end overlap, we've got the up-down, and we've got the forward-backward. Those are our 3 bonds that we're forming here for our sp hybridization. What is the hybridization of carbon in CO2? To figure out the hybridization of carbon in CO2, we could do a Lewis structure. We're going to have carbon in the middle, the oxygens on the sides. They'll need to get bonded together. We'll end up placing all of the rest of our valence electrons on the oxygens, but that leaves carbon out of some electrons, so we have to move some in. We'll end up with double bonds between the carbon and each of the oxygens. How many electron groups do we have connected to carbon? How many clusters of electrons are connected to carbon? Clusters or clumps. Our options range from 1 to 6. That's like the maximum amount that we've seen so far. What things are on carbon? Like what electron-related things are touching carbon? Double bonds. How many double bonds? 2 double bonds. So we've got 2 electron groups because we've got 2 double bonds. Double bonds count as 1 group, triple bonds count as 1 group, single bonds count as 1 group, lone pairs count as 1 group, lone electrons, radicals count as 1 group. So we've got 2 types of things, or 2 different things. They're both double bonds. And so we're going to need 2 hybrid orbitals. Which of these 3 options has 2 orbitals in it? Total of 2 letters. A, because it's S and P. sp2, because we've got two p's, we got one s and two p's, that would be 3 hybrid orbitals, which is too many. We don't need that many, we just need 2. If we had a lone pair, maybe. If we had 2 lone pairs, then we might do the sp3. But in this case, we've just got the 2 things attached to it, so we're picking sp. We can also have more than just sp3. We can have sp3d and sp3d2. So in our Lewis model, elements in the third row and below can exhibit expanded octets. And again, this is because they have access to d orbitals. I've talked about those as being extra pockets that they can put the electrons into. Oh, we filled up our s and our p. Let's throw some up into our d orbitals, and that works. As long as they're in the third row or below, they have access to those d orbitals. In valence bond theory, we're hybridizing some d orbitals. This is similar to, like, we need more pockets. We're just looping in some of those higher energy d orbitals. They're close enough that we can access them. So if we combine an s, 3 p's, and 1 d, we put in 5 orbitals. So we get out 5 orbitals. And the hybridization tells us the 5 orbitals that we put in. We put in an s, we put in 3 p's, and we put in 1 d. And this has trigonal bipyramidal arrangement. This is what I've been referring to as the basic shape for 5 electron groups. And it's always going to be that shape for sp3d. We've also got 4 unhybridized d orbitals that are left over. We can do this, showing this for a Lewis structure for ASF5. Our Lewis structure, we show that we've got 5 things attached. We should still end up with trigonal bipyramidal geometry. If we do it in the valence bond model, we've got sigma bonds, direct overlap between our sp3d orbital from arsenic and our p orbital from fluorine. It's the p orbital from fluorine because of the electron or the orbital diagram. We've got the unpaired electron in a p orbital on fluorine, so that's the one that's available to bond, rather than using an s orbital, because we don't have an unpaired s orbital. We can also have sp3d2 hybrid orbitals, so looping in yet another d orbital. We're putting 6 orbitals in, so of course we're getting 6 orbitals out. 6 atomic orbitals in, 6 hybrid orbitals out. And this has octahedral geometry, which is our electron geometry for 6 electron groups. So the geometry that our hybrid orbitals takes is going to be the same as whatever our electron geometry would be, which is kind of nice. And that could look like this with SF6. So we've got our sulfur in the middle. Our sulfur, because it's got 6 things on it, is hybridized into sp3d2. So we've got a sigma bond between the sp3d2 of sulfur and the p orbital of fluorine. That's what this nomenclature is saying. So this is saying it's a sigma type bond because it's direct end-to-end overlap. We're always going to do a sigma bond first rather than, like, we would never start with a pi bond. We're always going to start with a sigma bond. It's between the sulfur and the fluorine. And it's the sp3d2 hybrid orbital from sulfur. For fluorine, we don't hybridize, we just use the atomic orbital. And it's the p because that's what's open. That's what's got something unpaired in it. So for figuring out hybridization and bonding schemes, how do we know which hybridization scheme best describes the orbitals for a specific molecule? For us, we're just going to base it on the electron geometry of the interior atoms. And this is accurate enough. This is good enough for us. We don't want to do the computer simulations and calculations and all that to figure out what it actually would be, because that involves extra tools. So for hybridization schemes, the number of electron groups that we have on our central atom is going to match up with the total count of our atomic orbitals that we put in. So if we have 2 electron groups, we need our s, and we need to add 1 p. Blend those together, we've got 2 orbitals. That's going to have linear electron geometry based on the number of electron groups. And the same pattern repeats. For the rest of them, I think I've pointed out what these are mostly like as we've been going through them. Number of electron groups matches the number of letters in the hybridization. It always starts with S, then we add P's until we're out of P's. 3 is the maximum number of P orbitals. And then if we still need more, then we add D on top of that. It's always in the same order. These are the only 5 options that we'll ever see. It's based on the number of electron groups. Number of electron groups that we have equals the number of atomic orbitals that we put into our hybridization. The number of electron groups also tells us what the electron geometry is, which is the orientation of our hybridization. Good flashcard material, perhaps. So if we want to do hybridization and bonding schemes, first step, we need a Lewis structure for the molecule. We need the Lewis structure for the molecule so we know how many electron groups are on the central atom. If you don't do a Lewis structure, you're going to miss if you've got lone pairs. And you might also get the bond order wrong for some of the bonds. You might think that they're all single bonds and there might need to be some double bonds in there if you don't actually go through the steps of creating the Lewis structure. So Lewis structures stay being relevant. And then we can use valence shell electron pair repulsion theory to predict the electron geometry around the interior atoms. That's going to be any of our simple shapes. It's going to be linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Those 5 shapes, these same shapes that we are seeing here. It's going to be one of those 5 shapes based on the number of electron groups. Once we've got that electron geometry, then we pick the correct hybridization, again based on the electron geometry, based on the number of electron groups. So 2 groups sp, 3 groups sp squared, 4 groups sp3, 5 groups sp3d, 6 groups sp3d2. 2 and 3 sort of go together. And then for 4, we would sketch the molecule. Start with one of our interior atoms and its orbitals, try to show the overlap, and label everything as sigma or pi notation followed by the type of overlapping orbitals. And I might put one of these on as a short answer question for our exam 4. So if we want to write hybridization and bonding scheme for XeF4, what do we need to start with? Lewis structure. So step 1. Lewis structure. We can start out with a skeleton. Xenon's going to be in the middle because that gives us the most symmetry, and also fluorine only likes to have one bond. So it'll probably look something like that. We also need our number of valence electrons. Xenon is a noble gas. It's really big though, so it does do a little bit of bonding. So that's going to have 8 valence electrons because it's a noble gas. Fluorine, we've got 4 of them. They have 7 valence electrons each. That'll give us a total of 36 valence electrons, 8 plus 28. To get everything connected, we need to throw in some bonds. So we're going to start off with 1 bond each. That's 4 bonds, which is 8 bonding electrons. So we've got 28 remaining electrons. And now we want to start filling in our valence electrons from the outside, working our way in. So our fluorines each already have 2 electrons. How many electrons are we trying to get them up to? 8. So we need to go from 2 to 8. That means we're adding 6 to each. And that's 6 to each of the 4 fluorines. And we've got 4 electrons left. Where could we possibly put those electrons? On xenon. Xenons are really big. It's got access to expanded octets. And so we're going to put those on as lone pairs. So this would be our Lewis structure. If we didn't do the Lewis structure, we probably would have missed that there's 2 lone pairs on xenon. Now we need to figure out electron geometry. How many groups, how many electron groups do we have on xenon? 6. So we're looking for 6 groups. That 6 is made up of 4 bonds and 2, we'll write out lone pairs. The type doesn't matter for us for this particular question at this time. So our electron geometry for 6 groups is going to be octahedral. We also need to get the correct hybridization for 6 groups. What is our hybridization going to be for 6 groups? If we have 6 groups, how many hybrid orbitals do we need? It's also 6. Yeah, 6. So we need 6 hybrid orbitals. What's the first orbital that we would start with for hybridization? S. How many S do we have? Just 1. We need 5 more. And then next is P. How many P's can we have? 3. So we've got how many hybrid orbitals so far? 4. We need 2 more, so we're going to have to tap in to our D orbitals, and we need 2 of those, so the hybridization is sp3d2. And then we have to sketch the molecule and show the overlap with orbitals on our terminal atoms, label our bonds. So this one, because it's 4 bonding groups and 2 lone pairs, this will take on a square planar geometry. So I'm going to actually sketch it in like this. So we're going to have our xenon in the middle, and its hybridization, if I can move everything, scoot. Our hybridization is going to have a group up, a group to the left, a group to the right, a group down, one coming out, one going away. The one coming out and the one going away look kind of funky, unfortunately. So this would be our hybridization around xenon. And then we've got our fluorines that are in there also. What atomic orbital does fluorine have that's available for bonding? S or P? P, why P? It's what we were doing before. The reason that it's P is if we look at an orbital diagram for fluorine, it's going to look like this, S and P. And in valence bond theory, the unpaired electrons can bond. So P is available to bond. So that's why it's a p orbital rather than an s orbital. So give them their little peanut-shaped orbitals. They should actually be overlapping. Doop. Boop. Beep. So it looks something like that. That's step 4. And then we have to describe, for step 5, all the bonds are the same, so we can just describe one of them. What kind of overlap do we have between our xenon's sp3d2 and our fluorine's p? Is it direct overlap or is it that side-to-side overlap? It's direct overlap, so it's going to be sigma. Also, we're always going to start with a sigma bond first. So this is a sigma bond. It's between xenon, and the orbital that we're using is the sp3d2, and that's bonded with fluorine. Fluorine is bonding with p. So that would be our hybridization and bonding scheme. All right, let's look at a hybridization and bonding scheme for HCN. We would also need to do a Lewis structure for this to save us some time. I'm going to shortcut us to the Lewis structure. So our Lewis structure is going to look like this. This is HCN. Triple bond between the carbon and the nitrogen. Everyone's got happy octets. How many electron groups do we have on carbon? Yeah, it's 2. What geometry would that give us? Yep, it's linear. And if we have 2 electron groups, that means that we need 2 hybrid orbitals. So we're going to start with S. That's 1. We need 1 more. P. So it's sp hybridization. On the carbon. And then we can sketch in what does it actually look like. So for carbon, we're going to have our sp hybridization. These are the side ones. Those are our sp hybrid orbitals. And how is hydrogen going to bond with carbon? Which atomic orbital can hydrogen use? What does our orbital diagram look like for hydrogen? How many s orbitals do we have? We have 1 s orbital. How many electrons do we have in the s orbital? Also 1. We just have 1 electron. So we only have access to the 1s orbital, and so it's going to be an s orbital. So it's just going to be hydrogen in a ball overlapping with that. That's how we've seen it in the previous drawings. And then nitrogen, what's our orbital diagram for nitrogen look like? We've got to figure out how we're bonding there. For nitrogen, it's got 5 valence electrons. If we draw in our sp blocks, we got to fill in 5. That's going to fill up our s. We've got 3 left. Our p is going to be up, up, up. It's our moment. So we've got 3 p orbitals that can bond. And so nitrogen is going to be using its p orbitals. So one of them will be going out like that. I'll scooch it over so it overlaps. We've got 2 more bonds that we need to draw in. We've used our sp hybridization already. Both of our sps are used. So what can carbon use then to do the rest of the bonding? Do we have more p orbitals? We blended one of them, so we still have 2 unhybridized p orbitals. So that's what carbon's going to be using. Nitrogen also has the p orbitals. So we've got a pair that's up and down. We've got a pair that's side to side. And these are going to link up. The up to up ones do that weird sideways orientation bonding. That's how we add in our double bond. Our third one, let's do this overlap in fuchsia. So these are the forward-back ones. They're also doing the side-to-side overlap. That's our third bond to make it a triple bond. And then our labels for everything, between our hydrogen and our carbon, we've got a single bond. Single bonds always start out with sigma, or are always sigma. That's between our carbon with the sp and our hydrogen with an s orbital. And then we've got two other bond types. We've got the carbon to nitrogen bond, this one that's direct between them. That's end-to-end overlap. Maybe purple will show up better. Maybe better. That's direct overlap. That's our first bond. So it's carbon sp to nitrogen p. And we've also got, last but not least, these two pi bonds that are carbon p to nitrogen, also p orbital. Arguably the drawing part is the worst. I like the drawing part the least, at least. Questions? I'm going to skip the one for CO2 so that we can move on to molecular orbital theory, because this is probably going to end up being a slightly larger thing than doing the hybridization. So we've been doing valence bond theory. There's also molecular orbital theory. So valence bond theory, we just hybridize our central atom. In molecular orbital theory, we're doing orbitals for the entire molecule instead of for atoms. So this is orbitals for the molecule. We are going to be sticking to simple cases for molecular orbital theory. If you take more advanced chemistry, like Chem, inorganic chemistry, Chem, some of those you'll probably see molecular orbitals show up again. Solving the Schrodinger equation, even for simple molecules, is impossible, so we use trial functions. Computers come up with those, and it's optimized for the lowest energy, so we don't really have to worry about it. We're just going to use some basic patterns that we know of thanks to computers. Our approximation, our simple trial function for molecular orbital theory, is LCAOs, linear combination of atomic orbitals. It's a weighted sum of the valence atomic orbitals. It works pretty well. It's not that complicated compared to other methodologies. So we're going to combine the valence atomic orbitals of all the atoms together. So we're combining valence orbitals to form molecular orbitals. We'll see what these diagrams look like in just a sec. Couple slides. So LCAOs are often delocalized. This linear combination of atomic orbitals get shared along the entire molecule versus our hybrid orbitals that stayed just on our central atom. If we look at H2, we are basically just going to be looking at diatomic molecules, so it's just combining two things together. In more advanced chemistry, you'll add more things together and it gets considerably more complicated. So for H2, because the hydrogens are the same, their atomic orbitals are at the same energy level. One of the molecular orbitals is a sum of the 1s orbitals. And that's our bonding orbital. We call this sigma because of the shape. So we take our 1s and our 1s and we add them together. They're negative in energy. Bonds are negative energy. They're stabilizing in energy. So that's why when we add them together, the energy goes even lower. So we get a bonding orbital, and it's this direct end-to-end overlap. It's still that sigma shape that we saw before. It looks a little bit different, but it's still that end-to-end connection. Our orbitals are in phase, and it's lower in energy because bonds have negative energy, stabilizing energy, so it's lower. And we give this the name sigma 1s. Sigma because of the type of overlap that we have, and then the subscript, the 1s, because we're putting the 1s orbitals together. Now something new is we also have to get another molecular orbital out. So we're putting 2 atomic orbitals in. We have to get 2 molecular orbitals out. The first one that we got was that sigma 1s. The other one that we get is if one of the orbitals is in the opposite phase. And so we subtract. It's negative. So this is a destructive interference pattern because they're out of sync. So this is anti-bonding. This is out of sync. This is higher energy. So our energy level goes up, and this would still be sigma because of the shape, the way that they interact, but now it gets this star designation. The star, or asterisk, means that it's anti-bonding. So anytime we have an out of sync or anti-bonding arrangement, it's going to have the little star thing in the top right corner. And this is the negative pair to our sigma 1s. So our 2 options, when 2 atomic orbitals get added together, they have the bonding orbital that's lower in energy. So that's what we're showing down here, 1s plus 1s. They bond, they get along. That's our sigma bond. That's lower in energy, it's stabilizing. There's a connection that's made. The anti-bonding orbital is going to be higher in energy. These are out of sync. They're not getting along. It's destructive interference. This is our anti-bonding. There is always one bonding and one anti-bonding. For molecular orbitals. So anytime we're making molecular orbitals, we're going to get one bonding, we're going to get one anti-bonding. One of the ways that we might imagine this occurring, the way that these molecular orbitals are formed, the atomic orbitals, the atoms are coming together, and there's 2 different possible outcomes. Think of you meeting another person, just another random person. You approach each other for the first time, and you go in for a greeting. That greeting might be a fist bump, it might be a handshake, it might be a high five, but you go in for some sort of physical contact greeting that works best here for analogy purposes. So you go in for a fist bump, the other person also gives you a fist bump. Nice, that's a good start. Or you go in for a dap, and you hit an epic dap, and it's loud, and it feels good. And you're like, okay, this is a good start, this is a good foundation. That's our bonding outcome. There's an alternate universe where you go in for a fist bump and they go in for the high five and they end up turkeying you, which could be a good start, but usually that's just going to be awkward. Or you go in for the fist bump and they're going in for the handshake, and then you switch and they switch, and it's an awkward. That's not a great start. That's the anti-bonding outcome. So you went in for a fist bump and they went in for the high five. That's the anti-bonding outcome. That's essentially what we're doing with these linear combinations of atomic orbitals. The way that we draw the diagram looks like this. This is our general diagram. So we've got our energy axis. It's always going to be increasing in energy going up. So you just write energy, you draw an arrow pointing up. We've got an atomic orbital from our first thing, our atomic orbital from the second thing. And then how do they mix together in the middle? There's that bonding outcome. That's the lower in energy. That's our sigma 1s. There's also the anti-bonding. We usually I write in just like one line. That's going to be our anti-bonding because that's higher in energy. We would also draw in for our atomic orbitals how many electrons they came in with. We have one valence electron. For hydrogen, it only has one electron. So we draw that in. We also have one valence electron for our other hydrogen because, well, it's also hydrogen. And then we make our bonding and our anti-bonding, and then we place our electrons into our molecular orbitals, starting from lowest and working our way up. So they're always going to fill in from the bottom up. In this case, we only had two to put in, and so we paired them up in the bonding orbital. We've got the one up, the one down, and then we're done. And so this shows us, because the bonding is lower in energy, it shows us that the atoms can lower their energy by entering into this bonding agreement. We can also calculate the bond order. The bond order for a diatomic molecule is the number of bonding electrons minus the number of antibonding electrons. So the number of electrons in bonding minus the number of electrons in antibonding. How many electrons are in a bond? A normal single bond. 2. So we're going to divide by 2. That 2 is the number of electrons in a bond. In one bond specifically. So that's what our formula is. For hydrogen, diatomic hydrogen, we have 2 electrons in bonding, right? 2 in our bonding. Our antibonding is empty, so we put 0 for antibonding. We divide it by 2, and we get out 1. So this means that we have a bond order of 1, the strength of one bond, a single bond. Or maybe more appropriately, we've got a single bond equivalent in terms of energy. Positive bond order will result or can result in a bond. Negative or 0 bond order will not form a bond. So we can use this to predict if chemicals will exist based on how their molecular orbital diagram looks. If we get a positive bond order, then we can predict, okay, that probably exists. It could exist. It might even exist right now. If it's negative or zero bond order, we would expect that it does not form. Positive bond order is like a good relationship. Negative or zero bond order is a hostile or neutral relationship. Why would you go hang out with somebody who just always says mean things to you? Unless you really have to, which is hopefully not the case for us. So positive bond order, bonding. Negative or zero bond order does not form. If we look at a helium molecule, our helium molecule, each of our helium atoms is coming in with a 1s atomic orbital, but they've got 2 electrons. It's going to have the same bonding and antibonding scheme. We put 2 of the electrons, one from each, into the bonding orbital, but we've got 2 electrons left. And so the other 2 would go up into the antibonding orbital. So the antibonding orbital is also filled. We take our 2 that are in bonding and our 2 that are in antibonding. 2 minus 2 is 0, divided by 2 is still 0, so our bond order is 0. There's no incentive for helium to form a bond because it's just as stable without bonding. Arguably, I think it's more stable without bonding. I think that's how it works. However, the helium ion, so we've got He2 but with a 1 plus charge. Now we've only got 3 electrons because the helium ion, the 1 positive helium ion, has 1 electron. We put 2 into the bonding, we put 1 into the antibonding. 2 minus 1 over 2 gives us a bond order of 1/2. That's positive, so this could exist. This is expected to be stable. It's not especially stable because its bond order is 1/2. That's not a very strong bond, but it should be able to, you should be able to make it or observe it somewhere. Questions so far about our LCAO, linear combination of atomic orbitals, MO, molecular orbital theory? So we can approximate molecular orbitals as a combination of atomic orbitals. We're going to have one bonding that's lower in energy, one antibonding that's higher in energy, and it's more high in energy than our bonding is low in energy. So there's a slight offset to the negative side. The number of molecular orbitals formed equals the number of atomic orbitals that are formed. So if we're putting in our s orbitals, we get 1 low, 1 high. It's the same number as we had before. When we assign electrons to our molecular orbitals, we fill them from lowest energy to higher energy and spin pairing them as we build up. We are going to follow Hund's rule if we have got molecular orbitals of the same energy. So for example, we'd fill them in, if we've got 2 electrons, we'd fill them in up, up, not up, down in one box. So we're going to fill in singly first with parallel spin, and then we'll match them up if we need to. Stable bonds, bonds that will form and last, require positive bond order. And our bond order calculation is bonding minus antibonding, the number of electrons in those, divided by 2. That's our bond order. So 102, slide 102 is a good review slide. We're not done. We're going to do more stuff. This is just our basic intro to bond order. So let's use molecular orbital theory to predict the bond order in H2+. So we've got one fewer electron because of that positive charge. Is it stronger or weaker than the H2 bond? So to start out, we'll put in our energy axis. And we've got two things coming in. We've got a hydrogen, regular old H, and it's 1s orbital. It's got one electron. We also have H+. You could put H+ on the left and H on the right, it doesn't matter. This is also 1s, but because it's H+, we've taken away its electron, no electron for H+. When these bond together, if they have a good outcome, that's our bonding. Molecular orbital. They could also have a bad outcome. So we're playing multiverse scenarios. They go in, they hit the dap, they hit the high five, they hit the fist bump, everything works out, that's our bonding outcome. We also have the scenario where they don't get along, our sigma star 1s. That's our anti-bonding orbital. We're going to fill in from our atomic orbitals, they're going to flow down into the bonding, and then if we have extra, we put them up into the anti-bonding above. We just have one electron, so that one electron is going to go into the 1s. So this is what our molecular orbital diagram would look like. And then we want to calculate the bond order. How many bonding electrons do we have? One. So we're looking at how many electrons do we have in this middle zone, because these are our molecular orbitals. So we've got one. Do we have any in the antibonding? We do not have any in the antibonding, so it's 1 minus 0. And then our equation tells us to divide by 2. We end up with a bond order of 1/2. Is that stronger or weaker than H2? H2 had a bond order of 1. It's weaker. So that's period 1. We can also do this with period 2, homonuclear, just meaning they're the same atom, they're the same nucleus, diatomic molecules. So homonuclear diatomic molecules, molecules made up of two atoms of the same element of the same nucleus. The next set of molecular orbitals is also approximated by a linear combination of atomic orbitals. Instead of 1s, we're going to 2s now. So if we look at lithium atoms, lithium brings in one electron. It's an alkali earth, or it's an alkali metal. It's from the 2s instead of the 1s. Notice that our bonding, our molecular orbitals in the diagram, it's the same as 1s. It's just now it's labeled 2s. And our sigma is 2s, and our sigma star is 2s. So it's the same structure anytime our s orbitals are coming together. They're all very similar. I'm not saying that they're exactly the same, because there are ways that they can be slightly different. But the ones that you'll see, the ones that you'll make, are all going to look the same. Because we've got a bond order of 1, lithium, diatomic lithium, is predicted to be able to exist. and it apparently exists in the gas phase. Beryllium, on the other hand, is predicted to be unstable because we've got 2 electrons in the bonding, 2 electrons in the antibonding. That gives us a bond order of 0. And 0 or negative means should not exist. When we move up to add in our 2p atomic orbitals, we're also going to combine these together. So we're imagining we've got our 2 atoms sitting next to each other. We are going to call the internuclear axis, the one that runs through, that skewers the 2 centers, we're going to call that our x-axis. So the line that skewers them, that's our x-axis. And they're going to have their 2px orbitals, the ones that lie on that x-axis, that can directly overlap end to end. What would we call that kind of a bond? Sigma or pi? Directly overlapping it. Sigma. So this is our sigma situation. And just like with S, we get 1 bonding and 1 antibonding molecular orbital. Is that the only p orbital that we have? It's not. We also have our 2pz and our 2py orbitals that are 90 degrees to our 2px. So we also have to add those together. So we've got sigma 2p, sigma star 2p, that's our direct overlap. We also have our other 2p orbitals that would be parallel to each other, so they get the side-by-side overlap. So if we're looking at our 2py, these can overlap side to side, and if they get along, that will be the bonding. If they don't get along, that's the antibonding. But now these are pi because they're side-to-side overlap. And our 2pz is going to be the up-down version of this. If you just rotate this 90 degrees up, that's going to be our 2pz overlap. And that's going to be the same pairing of energy. It's just now that it's bonding up and down instead of front and back. The energy ordering for these is not all the same for all molecules. For period 2, we've got boron, carbon, nitrogen that have a different order than our oxygen, fluorine, and neon. Our typical ordering is sigma, next highest level pi, then our pi star, that's our antibonding pi, and then our sigma star. This is normal. This is what we expect to see. Our sigma is the lowest, and because it's got the most stabilization when it's bonding, our sigma star has the most antibonding. It's more high energy because of that. And our baseline would be here. I'm not entirely sure why I'm drawing this out because it also shows up like the very next slide. But it's symmetrical. So sigma, because it's that end-to-end overlap, that's the best overlap. That's going to be the best bonding strength. It's going to be the most stabilization. The antibonding is also going to be the worst because it's end-to-end direct overlap. This is like having a bad interaction with somebody in person versus pi star is having a bad interaction with somebody online. Arguably worse when it happens in person. So our expected order over on the right, our 2s is the same as what we've seen before, nothing new there. The 2p is where the new stuff comes in. So our sigma is the lowest in energy. We've got 2 pi's that are a little bit lower in energy, but not as good as our sigma, our antibonding, and then our sigma antibonding. The one that's weird, the ones that are weird, are boron, carbon, and nitrogen. The mnemonic is be careful now, which I imagine in like an old-timey voice, be careful now, for some reason. And the reason that this one's weird is because the sigma bonding and the pi bonding are flipped. The antibonding is the same. So that's why it's be careful now. The reason for that is the way that the s and px orbitals mix together. It's very complicated. Basically, the px and the ps interact a lot more because of like the sizes that they are, and that causes the energies to flip. All right, what we're looking at here, we've got B2, C2, N2, O2, F2, Ne2. So we're working our way across the periodic table from boron to neon. And we've got our orbital diagrams, just the middle part. We're not looking at what's going in. For all of these, we've got canceled out sigma 2s and sigma star 2s. They're both full. So the bond order is just based on the pi and sigma from the 2p. The boron we expect to have, it's going to have a bond order of 1. Carbon, we add in 2 more electrons, bond order of 2. Nitrogen gets a bond order of 3 because we've got 6 electrons that are bonding, no antibonding. When we move over to oxygen, now we've got 2 electrons that are in antibonding. So we do 6 minus 2 divided by 2 gives us 4. Or sorry, gives us 2. 4 over 2. We take 1 more away, and then neon's got a bond order of 0. And we can see that our highest bond order has the highest bond energy as well. We can also bring paramagnetic and diamagnetic into this. So we know from experiment that oxygen's paramagnetic. There's some links here to them showing liquid oxygen suspended between 2 magnets. If it's paramagnetic, then it's attracted to a magnetic field. And that's the result of unpaired electrons. So we can also predict paramagnetic and diamagnetic for these. So we're working with N2 plus, and we're doing an MO diagram, molecular orbital diagram. On the left, let's put our nitrogen, and on the right, we'll put our N plus. Our nitrogen is going to have 5 valence electrons. It's going to have 2 in the 2s, and the 3 remaining ones go into 2p. Nitrogen's one of our be careful now. It's the now, and so that's why our sigma 2p and our pi 2p are flipped from what we would expect. It's not symmetrical. Our nitrogen with the 1 positive charge only has 4 valence electrons, so that would fill in this way. We then have to fill in our molecular orbital spots. For the 2s, these both fill up. So the sigma 2s, the sigma star 2s, sigma 2s, sigma star 2s, both fill up. And then up top, we've got 5 electrons to place. So we can place 1, 2, 3, 4 into the pi 2p. And we've got 1 more electron left. That'll go into the sigma 2p. So do we expect the bond what's the bond order, first of all? How many bonding electrons do we have? There's two possible answers that I could expect you to give for this. How many electrons do we have in bonding molecular orbitals, things that don't have the star on them? We've got at the bottom 2, plus another 4, plus another 1. We've got a total of 7. So one scenario, we've got 7 bonding. 5 up top and 2 down below. And then how many anti-bonding do we have? It would be 2, because we've got 2 in the sigma star. This is if we're counting everything. We divide it by 2, and we end up with a bond order of 2.5. If you ignore the bottom one, because you recognize, well, those cancel out, so we can ignore those, then the other way that I would expect you to possibly count this is just looking at the top, 5 bonding minus 0 anti-bonding, also over 2, you still end up with a bond order of 1/2. Is that weaker or stronger than N2? If we add one more electron to make it N2 instead of N2 plus, is this going to be, is N2 plus weaker or stronger? Where would our next electron go if we had one more electron? It would go into the sigma 2p. That's a bonding electron. That would increase our bond order. So N2 plus is weaker. Weaker? Weaker. N2 has a bond order of 3. And then the last question that we've got here is N2 plus diamagnetic or paramagnetic? Are all the electrons paired, or do we have some unpaired electrons? Remember, we're just looking at the molecular orbitals in the middle. Are they all paired up and down? Do we have some unpaired? We have one unpaired, right? We got an unpaired one. So we've got one unpaired. Is that paramagnetic or diamagnetic? Para sounds like it means paired, but para is for parallel. Diamagnetic means opposites. Diamagnetic is when they're paired. Paramagnetic is when they're unpaired. So N2 plus is paramagnetic. So we would expect it to be attracted, slightly attracted at least, to a magnetic field. There's also heteronuclear diatomic molecules. We're just going to talk about it. We're not going to do examples. I'm not going to test you on heteronuclear diatomic molecules. So if we look at NO, oxygen is more electronegative. Oxygen is shown here on the right. And so the orbitals are lower in energy. So higher electronegativity leads to lower energy atomic orbitals. It doesn't really affect that much the way that the molecular orbitals go together. It does mean that the oxygen, because these are lower in energy, these are contributing more to the bonding. And nitrogen, because they're higher in energy, they're closer to the antibonding, so it's contributing more to the antibonding. Doesn't really matter for us. Fluorine can also do some funky stuff. It's so electronegative. Hydrogen's not that electronegative. So the 2p atomic orbitals interact with the hydrogen atomic orbitals rather than the s orbitals coming into play. Again, not super important. We'll skip that. For polyatomic molecules, which we're not going to do any MO diagrams for, neither Lewis nor valence bond theory predict that ozone has two equivalent bonds. If we do molecular orbitals, though, our MO theory, molecular orbital theory, predicts that those electrons are shared evenly. They're delocalized across these three oxygens. So this would give us equivalent bond strength. And this also works for things like benzene. Our Lewis structure, or Lewis model for benzene, gives us two resonance structures. The double bonds are always alternating. We can rotate them one position, and that gives us the other one. In reality, we've got delocalized electrons over that whole surface, and that's how benzene actually exists. It makes it really symmetrical. It's also flat, and it can actually slip in between DNA because it's flat and small, which is how benzene can give you cancer, can mess with your replication process for your DNA, which is why we don't use benzene a lot in student labs. Questions at all? We did it. We're done with chapter 11.